In neural networks, there is this concept of polysemanticity, where a single neuron has several functions. And this has parallels to evolutionary biology, where the term is pleiotropy, Greek for many paths. A pleiotropic neuron is, a pleiotropic gene is a gene that has many different functions. And because there are about 50,000 genes in the genome, and the human body has many more than 50,000 functions that it needs to play, genes are extremely pleiotropic. And there is another term from the psychology of problem solving. There's a Wikipedia article. It's not a very popular term, I suppose. And the term is polytele. It's Greek for many goals or many end states. Many ends. And that is just the idea that if you're optimizing a thing for many different purposes, that is polytelic. If, for example, I want my food to be both cheap and tasty and nutritious, that is polytele. I am searching for a single food I can eat which has all those properties. And this is difficult if those goals or search criteria are independent, because then the probabilities of a particular item that you're a candidate, a particular sample from the distribution, the probability that if those criteria are independent, then for each sample, the probability that it is high in each of the criteria are multiplicative. And so this means that the more criteria you require, the more independent criteria you require from your sample, from your particular food item, the probability of scoring, exceptionally high on each dimension decreases exponentially the more criteria you're requiring it. The more search criteria you have. So that's polytele. Now, I wanted to talk about the brain. So imagine you have 10 neurons. And okay, so in the context of artificial neural networks and deep learning, there are many people who are trying to optimize their neural nets to be monosemantic, interpretable, such that you can look at a particular neuron and decode what is the function of this neuron. And they want to optimize the network such that for every single neuron, or they want to optimize the network to be closer to the state where you look at a neuron and if it fires, you know what it is doing. That is a desirable property for interpreting what the network is actually doing. So for example, if there's a neuron that activates every time the AI is thinking about deception, that is very useful for alignment and many purposes. But it is very unrealistic. So here's why. Imagine you have 10 neurons, and you require of these 10 neurons that they only encode 10 different functions. So this is very interpretable, as I said. So 10 monosemantic neurons has space for 10 different functions, or 10 different memories, if you want to think about the brain. Okay, 10 different neurons, capacity of 10 memories. Now, instead of requiring the network to be monosemantic, imagine that you instead encode memories into each permutation of these 10 neurons. Now you have 10 factorial number of memories that you can store into the network. And some other number, very large number, for if you encode, more realistically, if you encode each memory into each combination of these 10 neurons. So, because you want to be able to, it is better if you have space, if you have memory capacity to store the 10 factorial, or the combination of 10 neurons, rather than just 10 functions per 10 neurons. So by allowing for polysemanticity or pleiotropy or polytely in your neurons, you have a much wider capacity, or larger capacity, for storing memories or storing functions in your network. And this is why trying to make it be monosemantic and interpretable in this manner is unrealistic and has a huge alignment tax. Yes. There was another thing I wanted to say, which was, in the brain, obviously it's polysemantic, and you have, if you imagine a cluster of 10 neurons, you don't have, what's it called? The combination of 10 combinatorial, whatever. You don't have that many functions in each set of 10 neurons. Instead, most of the combinations of 10 neurons go to making the slope for the activation of a particular function or a particular memory. I will say memory, that it's easier to think about. So instead of, if you imagine the space of all the, so if you have 10 neurons, then most of the combinations of those neurons go to pushing the network slightly further to the closest combination which actually serves a function. And this allows you to have a large room for error in the state. A large room for error in order to recall a particular memory. This is known as a Hopfield, or this one implementation of this is a Hopfield network. And I'm pretty sure the brain is a fractal, recursive, immense Hopfield network, where there's Hopfield networks inside Hopfield networks. And so what this, because you have many different combinations, and most of them go to pushing the state slightly closer to the closest state that has a function every time, then you can activate the ensemble of 10 neurons, and you don't have to be so precise in order to get the function you want. Instead, you can hit the border of this slope, like if there's a slope, and your external activations activate the ensemble at like the corner, then the network itself, if this activation has a lot of salience, a lot of power, then the local Hopfield network, the ensemble of 10 neurons, will rearrange and descend the state down to the minimum, and once it's at the minimum, that's when the function has sufficient power to trigger other functions. Right? So there's an input that's wide and has a large room for error, and then as long as the network is has input for long enough in order to resolve into its minimum state, it also has an output. So input, which has a large room for error, and an output, which leads into another Hopfield network, which may or may not, like the output aims at some other Hopfield networks, and the precision at which the output hits those Hopfield networks or concepts or memories may not be precise themselves. So that's what I mean by recursive Hopfield networks. Memories arranged in recursive Hopfield network. This is how you have several layers of abstraction too. So I might think about Norway, or if somebody asks me, yeah, I know this question, I know the answer to this question, but imagine I didn't live in Norway. Imagine I lived in some other country like America, and somebody asks me, where is Oslo? In what country is Oslo? Then I might start to think, Oslo sounds familiar. It's somewhere up north in Europe. Yes, somewhere up north in Europe. And at that point, we're at the minimum of a Hopfield network, a highly abstract, large Hopfield network. And once we reach that minimum, now next step. Okay, northern Europe. It must be Scandinavia. That's the minimum of another Hopfield network. And then Scandinavia, is it Sweden or was it Norway, or is Iceland even part of Scandinavia? Oh, Stockholm is part of Sweden, right? So Oslo must be in Norway, and that is the minimum of a deeper Hopfield network. And at this point, how do you recognize that this is a sufficiently specific answer to the original question? I am uncertain. I have some theories, but I'm not going to talk about them because I've already mentioned some cool points. And thank you for listening to my ramble.